let's get started. Thank you for that introduction. So I'll be presenting a talk on coupling soft computing and geospatial technologies for natural resource management. And in my lecture today, there are three key words here. One is soft computing, geospatial techniques, and natural resource management. So let's kind of go over them so that we can see how these three can come together synergistically to create solutions for natural resource management. So when we talk about natural resources, there are a variety of different resources. My focus largely has been on water resources, but water has a very strong connection with every other aspect of natural resources, particularly land resources, oil and gas production, animal husbandry, agriculture, as well as urbanization. So as part of looking at water, I've also looked at these coupled systems to look at food, water, energy nexus. So what is natural resources management? You all know what NRM is, or natural resources management is. It is management of natural resources or nature that nature has provided us, such as water, air, forests, and other landscapes. So if you think about natural resource management more from a management perspective, and not natural resources per se, what we see is that NRM has two competing objectives. One is to ensure that we gain short-term benefits to improve the quality of life from these resources. So we use them wisely and judiciously so that we can take the maximum benefit out of it in the short term for improving our quality of life. But in the long term, we also have to be cognizant of the fact that any resource that we use today could potentially impact how much of that resource is available in the future for future generations. So we want to kind of balance these two approaches. So when we think of natural resource management, at least I like to take a perspective of it being a complex adaptive system. In other words, we have a resource, a system that we are interested in. This could be an aquifer, this could be a river, this could be an ocean, this could be the entire world if we want to. And in that, there is a resource unit that is of interest to us. This could be water levels or fish, so on and so forth. We have some sort of governance system that tells us what institutions look after this resource. And also, they try to manage certain users of this resource. Now, users of this resource need not be humans. They could be wildlife. They could be other environmental users that provide indirect benefits to humans. Okay? So there is quite a bit of feedback and interactions between all of these players. Am I still audible? Or?
Yes.
Okay. And then, so we are, of course, looking at natural environments, ecosystems, and the socio-political system on the other side. So this is what makes it complex, because there are several systems within this natural resource management system. So there have been several approaches put in place to look at natural resource management. There are several theories. I'm not going to list them all, but some of the main ones here are: one is using sustainability as a criteria. Sustainability essentially tells us that whatever resources we have today need to be preserved for future generations. And in that context, we can define two types of sustainability. One is what we call the strong sustainability, in that we preserve the resource itself as it is available today. So we want the same amount of that resource be available as it is today. And weak sustainability is another aspect where we are not really preserving the resource, but we are creating wealth using this resource, and exhausting that resource. With the hopeful, we are hopeful, however, that future generations can use this wealth and find either suitable alternatives or substitutes. So typically, weak sustainability is what people use when we have a substitutable resource, but many resources are not substitutable. So, so oftentimes we fall somewhere in between these two extremes. Another way that has been used to manage natural resources is what we call managed depletion. So we essentially deplete this resource over a period of time. Groundwater resources to a large extent are managed this way, particularly in overstressed aquifers, where we say, this resource is not going to exist after, say, 100 years or 200 years. What do we do? How do we manage to make sure that it's available over that time frame of interest to us? And of course, anytime you have natural resource management, you always look at the other option, which is the passive management or do nothing, and see how good is our management compared to this, the management strategies compared to this do nothing approach. So how do we really manage? So if you want to see, okay, here are some theories to manage based on sustainability, based on managed depletion, then what we define is the carrying capacity of the system. Carrying capacity essentially is a supply side management strategy. What it does is it says how much can be used, how much resource can be used on some period of time, a year, 2 years, 5 years, or whatever it might be of interest to us, without causing any long-term damage. And so this is the idea of carrying capacity. Carrying capacity was very popular technique, popular way to manage things way back in the 70s, about 50, 60 years ago. That's where it started its genesis. But the problem is not many places it has been used or used properly, so we are left with systems that are well past their carrying capacity. So they have been overexploited or overappropriated. So how do we manage these stress systems becomes an issue. So when we have a stress system, we tend to do more active management, and we say, or we do what is called the demand management. So we manage the demand that we are placing on that resource. And for example, there are fishing permits, grazing permits that are put in place to avoid overexploitation. Similarly, a lot of places in India, we regulate electricity in rural areas primarily to reduce overexploitation of groundwater resources. So there are different strategies, different ways in which we manage natural resources. The big questions are, is this resource exhaustible? Is this resource renewable? If it is renewable, are there threats to its renewability? Is that going to diminish over time? What are some of the factors associated with it? Some other incentives to look at, like the instruments that we typically use are either we use incentives like subsidies for water conservation, government infrastructure into wastewater discharges, because we take the water that's not suitable for a given purpose, and then we repurpose it using wastewater treatment. And then one idea is to encourage its use or its reuse through governmental subsidies. There are taxes and penalties which are used to correct market failures. For example, we put what is called as a sin tax. In water management, it's very common to give a certain amount of water for everybody to use for free, pretty much. But anything past that, you're taxed very heavily. The idea is to conserve water while making sure that water as a public good is available to all of us, because it's one of the basic necessities. So penalties for causing pollution is another way of taxation or a penalty that's used to correct market failure. Of course, the key issue for any natural management that people have seen across the world and over last 40, 30, 40, 50 years is that public support and buy-in is very critical for any sort of management that we want to do of these natural resources. And this is one place where GIS, Geographic Information Systems, really has come in very handy because it allows us to put various layers of information, often from very disparate sources, and visualize their linkages or visualize how they form on each other. And that is really the most critical aspect of GIS and its success in natural resource management. So we've talked about GIS, so let's look at some other technologies, geospatial technologies that we use in natural resources management. And one thing to keep in mind is that by its very definition, natural resource management system or the natural resource management, if you take a systems or a holistic perspective, is a system of systems or a complex adaptive system. It is also called a coupled human natural. So clearly nature is one that is providing us a supply of what we want. Humans are the consumers of it. In doing so, humans might alter the system to a point where we cannot recover. And the idea of active management is to ensure that this doesn't happen. There is no catastrophe or a market failure from which we cannot rebound back. And if we have gone to that stage, then the question becomes how best do we preserve or protect or do whatever we want to do with this last stage or last mile of that system left with us. Right? So a lot of times we are able to rehabilitate these systems, deforestation, endangered species. That's one area where we have tried to rehabilitate systems. We have brought back many endangered species out of that endangered species list, partly through very active rehabilitation. We have done that for groundwater systems as well. We've switched cities from groundwater to surface water or conjunctive use, reduce the stress on one resource so that that resource is not overexploited just because it's cheap. And then we have used or helped that system regain some of its lost resource so that it's available in the future generations. So when we do natural resource management, we are talking about many different players and many different subsystems. For example, if I want to do a watershed management, which is basically understand how water, rainfall in that water percolates into subsurface water and then flows on surface and eventually discharges at a point. There are many users or many stresses on that water. The climate itself is a stress. In addition, anthropogenic uses are a stress, not just urban, but rural water supplies can also be fairly strong, especially for agricultural uses. And then there is water for energy consumption, water for other uses, recreational uses and such. So you can see that it's not just enough that we know what a watershed looks like or how a watershed looks, which we can do using GIS. GIS is one of the basic tools that we use to delineate these watersheds. It's also important to bring in information about climate, hydrology, land use, land cover, the human aspect, where is the water being used, how much water is being used, and then what about the environment and its need for water. This is becoming increasingly important as we understand that taking water at one location will cause a damage to another natural resource, particularly the drying of rivers can cause losses to diversity, biodiversity, loss of fish, and other things, which indirectly do impact humans again. So, so understanding this complexity is key to natural resource management. And what we need for that is models that integrate these various subsystems and put them together into a complete whole. Okay? So models play a very big role in natural resource management because we try to simulate what is happening with our system using models. These could be system dynamics models, this could be lump parameter models, this could be distributed models. They can be of varying complexity. But the idea is that we create a model of the system, and then when we create a model of the system, then we can stress that model in many different ways and see what are the potential impacts. And once we know what those potential impacts are, then we can come back and say, well, we don't want certainly this to happen. So what prevent that? Are there engineering controls? Are there administrative controls? Are there a combination of both that we can use? And also, if we have integrated models, we can also look and say, if this system is stressed, what happens to other systems that are interdependent on that? For example, if I start over pumping groundwater, am I going to cause depletions in base flow? Am I going to cause rivers to run dry? And if that happens, then what happens to the fish? What happens to the farming communities that live or sustain on that fish? So on and so forth. So you can see the complexity extends fairly quickly, but integration of these different models developed by hydrologists, by civil engineers, by geologists, by biologists, all kind of start meshing together into this larger umbrella of integrated water resources, or natural resources models, or INRMs. Some of the other things that have happened is historically a lot of natural resources were managed in a command control mode. In the command control mode, what happens is the government tells what can and cannot be done, and people enforce those rules. Like, the rules are enforced on people. A lot of times, what happens, what we've seen happen with that is, especially in countries that have a large federal structure, like in US or in India, the local issues are not very well captured. And because the local issues are not very well captured, what the government might be wanting to do on a very large scale may not really work at certain places because the local issues are not taken into account. So over the last 30 years or so, there has been a big push to move away from this command control type approach to more participatory, decentralized, bottoms-up approach, where we bring people who are actually using these natural resources and then find ways to get some consensus and build a solution that is more practical and that is more viable in that area. And the other thing that we've also seen is there is a push to move away from very large-scale engineering to more nature-based solutions whenever we can. So the last 30 years, we have seen two major shifts in natural resource management. The first shift was more towards the waning of these command control approaches, moving more towards decentralized participatory approaches. A lot of that work, a lot of excellent work going on in India, especially with watershed management and deforestation. So there are several natural resource management techniques that have come into play, even endangered species restoration. Those kinds of things have come out of this type of thinking. The second thing is we are trying to do more nature-based solutions than solely relying on engineering. So wetlands for water quality improvements, rain gardens for water harvesting. So these are some of few techniques that people are demonstrating, where we say, well, we also conserve water, but we also increase the lung space of the city or the greenery of the city because it is able to absorb carbon dioxide and create oxygen for us. So how do we reduce the carbon in this very large urban areas? Again, nature-based solutions give us some very good alternatives to do that. So these are the two big things that are happening with NRM. And when we want to do NRM, we almost need a model. There is no other way to do management because we are trying to predict something in the future. We are trying to take an action today with the goal that it is going to be useful as to what will happen in the future. Whatever disaster or catastrophe that has happened today is not going to get repeated, and hopefully we'll never get to that stage if we have never gotten to that stage. So for that, we use models. There are two basic types of models that we use. One are called the physics-based models. These use physical principles like conservation of mass, conservation of energy, conservation of momentum, the basic physical laws. They become the cornerstone of building these models. Good news about this is these types of models are very transferable. In other words, once I make this model, I can take this model and apply it to another watershed, for example. But not all parameters of these physics-based models are truly physics-based. Some of them are empirical approximations, so we somehow have to do some calibration to get those parameters. Or sometimes the physics-based models lump many processing into a single number, and then which has no physical meaning, so to speak. Then how do we get numbers for that is something we have to obtain via calibration. The other type of models are these data-driven models. They basically make use of observed data or data from controlled experiments, if there are any, and then use statistical methods to develop these models. The good news about these is they are a lot simpler to build compared to physics-based models, but they are not transferable as easily. So I will need the same type of data in another watershed if I were to build this model over again. So these types of models invariably need spatial data, because when we talk about natural resources systems, they have a spatial footprint. So if there's a spatial footprint, you have to account for variations in that space, or what is happening inside that space, trying to identify places in that space which are conducive to certain type of management, and other areas that are not conducive to that type of management and need some other type of intervention. So spatial aspects and natural resource management have had a long history of traveling together. A lot of spatial technologies were developed for natural resource management. One aspect is the satellite remote sensing. If you look at Landsat, the Landsat was actually sent out in the 1970s, 72, by NASA, particularly to get land observations, because they wanted to study how the landscape evolved or changed over the world, and that could have very profound implications on natural resources. How much deforestation is taking place, how much urbanization is taking place, how is agricultural land being converted to ranch land or vice versa. All those questions are what drove the development and deployment of Landsat models. NOAA ADHRR is another satellite that has had a very long longevity in one form or another, and that model was also that was also put out in the 70s to basically look at very coarse scale but at a very high temporal frequency to see what is happening. So to detect like some of the natural hazards like earthquakes, detect things like forest fire and stuff, which are again very useful for natural resource management. We have seen several products. GRACE is one product. GRACE satellite actually measures, it's actually two satellites that follow each other, and they measure the gravitational anomaly. Gravitational anomaly is usually caused when you remove large masses from the Earth. So a flooding in Amazon or in Ganges, or flooding in or groundwater pumping in Central Valley, California, or in Midwest. All of these cause gravitational anomalies. Even the large-scale groundwater pumping that goes on in India, in the northern part of India, that can also have gravitational shifts. So GRACE is another satellite that we use. So remote sensing plays a very key role, and it's a key geospatial technology that we tend to use. Our initial focus was more on what we call visible remote sensing or near-infrared remote sensing, which is what the Landsat, MODIS, and those kinds of satellites provide. But these days, we actually not just look at that part of the spectrum, but we also look at the longer wavelengths. Particularly, we are interested in large wavelengths such as the radio waves, the microwaves, and so on and so forth. So NASA and ISRO are collaborating to put a satellite out called NISAR, and NISAR should be, it has been delayed a couple of times, but it should be in orbit fairly soon. They're talking about June or so. And NISAR actually shoots microwaves. So when you have microwaves, the sun doesn't naturally give microwaves. So what it does is it shoots microwaves onto the ground and then looks at the reflection back. And one of the good things about NISAR is that it uses C-band and L-band. What happens with these higher bands is you're able to penetrate through the leaves and actually hit the ground, so you can measure soil moisture and other aspects like that. So you can look at how dry your system is, and that can have very profound implications on how you want to manage. Because if the system goes dry, that means that the plants are not getting enough water, so we could do irrigation, for example. If the forest ecosystems are going dry, then the chance of forest fires increases. So perhaps we can monitor that and spray some water or do other types of interventions that can prevent these very large forest fires, like the ones you might probably have heard about, the ones that happened in California very recently. So most of these models from remote sensing, we have largely used statistical methods to model these system behavior. So we take data from these multi-band data coming at different resolutions, and we want to use that data to, with statistics, to understand or model our phenomenon of interest. So I'll show you an example here from Texas. This is the work of one of my students. And what we were doing is we were looking at Landsat data and looking at the droughts that were happening in the system. So if you notice, this side is a wet year, and you can see like very dense network of streams flowing through, and then you will see a lot of riparian vegetation surrounding it. And this is 2011. 2011 is one of the worst single-year droughts we have seen in the state of Texas. And you can see that clearly much of our streamlines or creeks have diminished in size. We've lost a lot of vegetation here. This is basically cropland that did not survive the drought. But in general, there is a lot more greenery around these riparian areas because there is more water, and you start losing that. So by looking at two satellite images along with some ground truthing, we can talk about how resilient is this forested ecosystem to droughts, particularly can it withstand droughts. So we can look at Landsat imagery, we can look at spectral radiations, couple it with some aerial photography, and back out certain things like which species survived, which species didn't, why are they drought tolerant, why are they not drought tolerant, what type of mechanisms do they have for storing water and recycling water inside them, gives us very good understanding of how to manage these types of ecosystems in the future, especially if you're having a drought. And the projections for us is that our droughts are going to increase over time. So this becomes all the more important. Here you're looking at soil moisture, and you can see that the soil moisture derived is pretty barren, and wherever we have lost moisture, we have lost vegetation as well. So that again gives you the key linkages between soil moisture, forest ecosystems, and as well as agricultural ecosystems and how they interact with each other. We can also take data from this and do conventional statistics. So here I'm using copula theory. Copula theory is essentially, I'm looking at a climate change indicator called SPI3, or the Standardized Precipitation Index, accumulated over 3-month period. This basically tells us climate states, whether we are in drought state or a normal state or in a wet state, something like that. And then this NDVI, or the forested NDVI, tells us that the greenery associated with it, or the amount of greenery that we have. And based on that, we can actually connect climate to forested system and say what is the probability of this ecosystem or this watershed not being resilient to drought, given that we have a drought, is what I want to find out. And I can do that using Bayes' rule, which is basically the joint probability of not resilient and having a drought divided by the probability of the drought. I can derive these things from Landsat imagery data along with some hydrologic measurements that are happening in the site, so we can integrate those two. Geospatial data as well as some point estimate data, put them together and calculate what the probability is. And again, if the probability crosses a threshold, then we say, we need to do some active management, or this is what is going to be the impact. So remote sensing, GIS data, we can do a lot of statistical methods, almost any statistical method. Most common statistical methods that we have used are hypothesis testing, things like trend analysis, change point analysis. You can do it pixel by pixel, you can do it on a zonal scale, over zonal averages. Some things to keep in mind is, just like time series data, spatial data also have correlation structure. So the values, a common assumption in statistics is that all data are independent. In other words, if I take this sample and I take this sample has no impact on this sample whatsoever. So that's what independence is. But when we come to statistics, when we come to spatial information, from Taubin's law of geography, we know that everything is connected to everything else. Things that are closer are connected more. So if I have 2 points very closely spaced in space, then they're very strongly correlated, which means I might have 2 data points, but really the information that's combined is not equal to 2. They're not giving me 2 separate pieces of information. They're just giving me 1.5 or 1.25 or some level of information because of that correlation structure. So correcting for that correlation, there are several methods, but that's, I know that needs to be looked into. Principal component analysis, this is a strong data reduction technique, very standard way of doing it. Particularly if I have multi-band data, I take these multi-band data which will be correlated to each other, because if I have more green, chances are I have less red, so there's a correlation between them. Similarly, if I have green, chances are the infrared, I'll see very high values of infrared, or I'll see a lot of red because that's being reflected out in Landsat, for example. So putting these things together, what PCA does is it creates those independent or orthogonal data sets, which we can then analyze using conventional statistics. Clustering methods, they kind of cross over between modern machine learning and traditional statistics. That again is used quite a bit. Linear regression, nonlinear regression. These are very common statistical methods that we tend to use with GIS. We can take raster calculator or raster algebra and include this type of models and look at things happening on a very large spatial domain. So one of the advantages of these methods is they end up giving you algebraic equations, which are very easy to put into your raster algebra or raster calculator, and then perform pixel by pixel calculations and create maps of your output based on certain inputs. So in the next half, let's look at soft computing. So we covered what natural resource management is. We saw why geospatial technologies such as remote sensing, GIS play a very important role in natural resource management because they help us map a variable of interest. And when we use models, either we can embed that model many times into our GIS and create maps so that we can tweak the underlying model and see what will happen. So this is where GIS comes in very handy, because it gives you a nice spatial map of what's happening with a model in the background. So coupling models in the background with GIS creates the benefit of both technologies and makes it very useful, particularly for doing practical decision making or decision making in groups where people can change different numbers and see what's going on. So soft computing offers us another avenue. So we'll talk about soft computing and see how soft computing can be integrated with GIS to create new models, spatially explicit models. And I'm going to show you several examples moving through this and talk about some of the common technologies that are available these days for integrating. So what is soft computing? Soft computing refers to, again, an umbrella of technology, an umbrella term. There are many technologies that have come out of fields of artificial intelligence and human reasoning. So these are technologies that have come out from the umbrella of artificial intelligence and human reasoning. The idea behind artificial intelligence when it first started was that we somehow want to mimic human behavior in a computer. So we want to take a computer and we want the computer to act like human. So of course, the holy grail of that is we can think. Computers, by the virtue of the way they are set up these days, they cannot think. So how do we make these computers think is really what drove artificial intelligence. And while they were doing that, they realized that the computer, because of its computing power, was very good at doing certain things as opposed to others. So machine learning is a subset of artificial intelligence that has gained a lot of popularity in recent years, but it's been popular for a fairly long time, actually, that makes machines understand and process complex data sets, or create models using data to capture some highly nonlinear phenomenon that we observe in nature that we cannot traditionally capture with either physics-based models or statistical models. So soft computing can be applied to a wide range of problems. Machine learning is a subset, and the machine learning is largely used for classification and regression problems. Classification means you have a discrete output. Either there is an exceedance of contaminant concentration, there is non-exceedance, a species was observed here, species was not observed here. Those kinds of data sets where you have a discrete yes or no or high, medium, cold type data sets, those are discrete data, those are classification problems. And if you have a continuous output, for example, temperature, carbon dioxide concentration, even countable number of elephants in an area in a state, those are countably finite numbers. They're discrete, but they're countably finite. You can use regression type problems. And there are some genetic algorithms and other nature-inspired methods that also fall under this soft computing umbrella. Very useful to solve highly convex, non-convex optimization problems where you could have multiple local minimas and you want to identify one global minimum, the minimum of the minimum, if you may, from that subset. So gradient-based methods or the traditional methods don't do very well in that. The third aspect of soft computing deals with uncertainty. In statistics, you can deal with one type of uncertainty, that is, if I make repeated measurements, I should be able to get a good understanding, not the precise value. I should at least understand what is the range over which this parameter is going to vary, what is the most likely value, 95% confidence levels, those types of things statistics can give you, because it is looking at saying, I don't have enough measurements. If I make more measurements, I will get better understanding of the data. But not all uncertainty falls into that category. There are many forms of uncertainty where, for example, what is hot or what is cold can vary by perceptions, right? What is hot for me may not be hot for you. What's cold for you may not be cold for me. So, because the definition of hot and cold is not very concrete, it's not objective, it is a very subjective or a linguistic description of what's happening. So those types of uncertainties are called epistemic uncertainties. They're coming because we don't have a good model to say what hot or cold is. And what I think is hot will vary from context to context. You know, what I think is hot when I take a shower is very different from what I think is hot when I sip a cup of coffee. Can be two different things. So those types of model, fuzzy set theory and its variants do a very good job with that. So as you can see, soft computing spans over a variety of different fields. So how to cover everything in a single lecture. So I'm going to focus on a few of these techniques. But before we go, let's take a little detour into the history of soft computing. So soft computing is not new. The word itself may be new, but the idea of AI, machine learning, dates back to almost 1950s, post-World War II. There were a lot of computers, there was a lot of technology for that time, and people started thinking, can we really make, and they were also very cognizant of the fact that there were a lot of casualties from all places in World War II. So they said, can we make machines think like humans so that they can go fight wars for us? You know, so a lot of this was derived from post-war efforts. And one of the first ideas that came about was what is known as perceptrons. And what perceptrons does is it tried to mimic the function of the brain. So essentially, you know, you have some stimulus that you get. You touch a cup of coffee, so you can feel the heat. I'm also looking with my eyes. I see that it's a coffee cup, so chances are this has got some coffee in it. And the decision I want to make is, should I drink this coffee or not? And what a perceptron does is it takes all those stimuli that I'm receiving, weight it, and send it to this neuron. And what this neuron does is it aggregates all of this information according to the weights. You know, somehow my hand, in this case, what I'm feeling with my coffee has more weight because it's hot or cold, as opposed to me looking at the cup, because this cup can have water, it can have something else, right? So it gives different weights, and then it aggregates all those stimulus that has come to it, converts it into a function, and it then gives out a decision of yes or no. So it uses this tan H function, tan hyperbolic function, which essentially says yes, if certain conditions are met, no, if certain conditions are not met. So this is what is known as a perceptron. Perceptron was, there was a computer scientist named Marvin Minsky who came up with this idea, but he couldn't go very far because of the computational capabilities at that time. The second idea, although this idea had a lot of promise, it was able to do simple things. You could not link multiple perceptrons like we would in a human system. In a human system, you have thousands and millions of such perceptrons sending signals to the brain through neurons, and then the nervous system carries it to the brain and then carries back the signal that the brain provides, or the output that the brain provides. The first revival of soft computing came in late 1980s. 80s to 2000 saw that there was more power because of PCs. A lot of people could do a lot of things on their desktops. So we could start training and learning multi-layer perceptrons. Again, it didn't take off much, but the second revival really came in 2010s when cloud computing became very popular. And when cloud computing became very popular, we could put very complicated perceptrons and neural networks together, what we call as deep learners these days. So the deep learning models need to be trained, coming up with a good algorithm to train it. Jeffrey Hinton actually won a Nobel Prize last year for his work in physics, although he's a computer scientist by profession or an electrical engineer. So this is the second revival of soft computing where we are doing deep technologies or deep learning type technologies. Of course, all of this can be done in a spatial context. You can take any of these models and stick it with a neural network, stick it with GIS and use it in a geospatial context. Okay, it becomes very computationally intensive when you do that. You need some very powerful machines to run it. You have to exploit parallel processing and other types of computational technologies. But nonetheless, is it doable? Yes, it's doable these days. So there are these soft computing tools. There are hundreds of soft computing algorithms. We can cluster them or group them into 3 different categories. One is what's called unsupervised learning. This is where we use for clustering and grouping. Supervised learning, this is where bulk of the work is, looking at inputs and trying to map an output, map the relationship between inputs and outputs. And then there is also reinforcement learning, where we learn as we go. So there is something called pre-training and forced-training type reinforcement learning. The best example of reinforcement learning is an autonomous vehicle, like a self-driving car. You train it using reinforcement learning. Every time it takes the right turn, you reward it. Every time it takes the wrong turn, you penalize it. So it keeps on learning. You're training the model a little bit, and then continuously reinforcing good behavior and admonishing bad behavior so that it's able to do what it's supposed to do. So the learning kind of continues. So that's reinforcement learning. Again, all these 3 have found you can put all of these in a spatial context and use it. Clustering analysis, very common way to do unsupervised learning. One particular type of neural network that has got a lot of popularity with land use, land cover classification, and soil mapping and natural resource management applications is this self-organizing map or covenant network. Essentially, it is a 2D model, a rectangular grid of 2D nodes, and when it sends the data, for example, I'm sending MODIS data here, what it does is it takes these 7 inputs and triggers the neurons that it thinks best suits this data, that best represents this data. And once it does that, what it does is the weights change in respect to this new things, and the neighboring weights also change adapting to this new things. So what it does is it tries to, as I'm sending more and more and more data, it will organize itself, the self-organizing map. That's why it's called self-organizing map. It's a map because it's 2-dimensional in nature, and because it's 2-dimensional, each one of these can be a cluster. So each one of these can take a unique value. For example, sand, silt, clay, or rural, forests, those kinds of things. So used quite a bit for land use, land cover classification, and soil mapping purposes. There are something known as lazy learners, lazy learning algorithms. Essentially, what they do is they don't have a model per se, but they have these points. It says, let's say I want to evaluate this point X. What it does is it looks at all the neighbors and says most of these neighbors are red, so I'm going to call this a red. Okay? Similarly, it's going to look at its nearest neighbors and call it X. If I want to do a regression, get a value, what it does is it takes all of these values and then provides me with a weighted average based on the reciprocal of the distance. So the inverse distance weighting, very classic interpolation algorithm that's used widely in GIS, is nothing but a lazy learner. These do very well for interpolations. They don't do very well for extrapolations. They're not very good as predictive models, but if you want to fill holes, if you want to do interpolation, if you want to fill in missing data, this type of machine learning models play a very important role in giving you much better classifications than traditional inverse distance weighting, because I can raise this weight to some other power instead of just square power. So I could look at Euclidean distance, Manhattan distance, different types of distances to do specific to a problem. There is something known as rule-based learner. Rule-based learners are learners that use experiential learning. We all undergo some experiential learning. We have experience. We probably have burned ourselves touching the stove. So next time we do it, we say, okay, if stove, don't touch because you might burn, whatever, right? So we create this rule and use those if-then-rules to guide our decision-making process of how we predict certain things. And that is what rule-based learners try to do. There are many ways of doing this again. There is rule-based expert systems where you take a whole set of rules, stick it in a database, and then you fire relevant rules, you resolve any conflicts between the rules and come up with a solution. Association rule modeling is a spin-off of expert systems. In expert systems, you have to tell the rules before, whereas in association rules modeling, what we do is we give the data and let the model pick out its rules. Okay? So a lot of times ARM is done before we do expert systems. There is something else known as tree-based models, which are called classification and regression trees. So those types of algorithms are used quite a bit as well. Here's an example of a cart model. What this cart model is trying to do is it's trying to predict nitrate contamination in Ogallala Aquifer in Texas. This is the largest aquifer in the US. About 20% of that aquifer is in Texas. And what we want to do is we want to predict the risk of nitrate contamination using a whole host of other parameters such as depth to water table, nitrogen deposition, dry deposition of nitrogen, as well as other factors like nitrogen loading that is associated, like fertilizer use. So it takes and creates this decision trees. Here it's starting off with calcium, and it says if the calcium is greater than this, if it is true, it goes along this line. If it is not true, it goes along this line. Checks for this criteria, again, true and false. So it keeps going down the tree till it makes a decision as to what value should be given, or what state should be predicted for these things. So tree-based classification or tree-based models can be linked with GIS. I can see I created a model like this and stuck it with GIS, so I was able to predict what was happening at all these different points on this grid right here using these values. So we take a machine learning model and marry it with GIS to do what we want to do. There's other types of models called collaborative learning models. What these collaborative learning models do is they create many simple models and they use them in combination to create a solution, right? This is the way the real world works. This is how engineering and scientific agencies work. Not everybody does everything. We do some pieces, other people do some pieces. We bring them together and create a product. So the idea is that strength is in collaboration, and having a group of weak learners that can only learn one or two things is much better than a full one-stream learner. So we bind them together and get a model that's an ensemble model. Another word for this is ensemble models. So there are two types of ensembling that we can do. One is called boosting algorithms. Essentially, in a boosting algorithm, we start with a very simple model, and then we keep on adding more and more complexity based on what the model is doing. So we take the model, predict, make the errors, take the errors, create another model, make a prediction, and then take the errors, create another model, and each of these models contribute to my output, and they're weighted according to the errors, and that gives me a boosting algorithm. The idea is that you build a small model, take the errors, correct the errors, correct the errors, correct the errors, and keep moving. Bagging is more a parallel operation. What we do is we make a model, we predict, we take the data, make models, make predictions, send all the predictions and aggregate them, and then we make a prediction. So bagging type random forest is a bagging type algorithm, eta boost, very common, X boost, eta boost, gradient boost, so there are different boosting models that are available for use. One of the important things about these collaborative models is that they help you identify important variables. So if you have a very large data set, which we typically can accumulate, particularly if you have like MODIS, which has 30 bands data, or any other thing that has very large data sets, and we put them together, there's a lot of redundant information in there. So how do we pick those parameters that give us the biggest bang for the buck? That's what this relative importance scores do. You can use boosting and bagging to do these things. Similarly, you can use ensemble models to make predictions. Here I'm using gradient boost and random forest to make predictions. They do much better than doing it with CART, Mars, and other schemes. The last one I want to talk about are ANN models. ANN models mimic the function of the brain or the central nervous system. As I said, these build on this idea of perceptrons that I talked to you before. Basically what this is a synapse. These dendrites. These dendrites receive stimuli, and then they take the stimuli, pass it to a neuron, and then the neuron passes it on to other neurons, and eventually to the brain. And then once brain makes the decision, the central processing unit, it transmits it back and says what you need to do, gives you a response. So the way it is done is you first aggregate all your stimuli, run it through some activation function, and then calculate an output. Multi-layer perceptrons essentially stack multiple layers of such perceptrons to create very deep neural network models. So this is called your input nodes. These are your hidden nodes, hidden neurons, and these are your output neurons. This is what we want the model to predict. And you can see that there are two levels of hidden neurons that take this and then give this information. So the more layers of hidden layers we add, the more deep our model becomes. And more deep the model becomes, the more closely it mimics the brain, but the more difficult it is to calibrate such models. And really that was the key factor that stopped research in 2000. That people knew that deep neural networks were able to do much better, but they just didn't know how to optimize or get the weights or fit this model to data. And in 2013, 2012, people came up with newer algorithms that were able to do it, something called greedy learning algorithms, and that really helped revolutionize. That's why we are seeing a resurgence of deep networks and deep learning these days. Again, they can be used for both classification and regression problems. One downside of neural networks is they're largely black boxes. All the information that's there between input and output is encoded as weights, and we really don't know what these, how do we interpret these weights, what does that mean, are some questions that need to be still explored. There are some, the more complex the model becomes, the more difficult it becomes for us to look at these things. So ANNs can be used with geospatial computing. We can create 2D surfaces, 3D surfaces using ANNs. And actually they can be used as surrogate models for physics-based models. So one of the works that I did was we took this regional groundwater flow model, which is a partial differential equation. We took a two-dimensional partial differential equation, and then we tried to model this using neural networks. Okay, so we take this idea that if you want to model groundwater, you need to have some aquifer properties, you need to have some persistence that you will see in groundwater, because groundwater is a very slow-moving process. There is some spatial dependence that we need to capture, and then there is some stresses that we need to capture, and everything else that we want to capture can be captured using this bias term, and then we send it through the neural nets, and then we get the predicted water level change, and then from the hydraulic head we can calculate, from the previous hydraulic head we can calculate the hydraulic head at any given time. So, so if I put X and Y, I can create a 2D model. If I put X, Y, and Z, I can create a 3D model using neural networks. And one of the good things is we could use another technique, the random forest or the tree-based classifier, to identify which parameters, which lags, which nearest neighbors should we take to model this regional groundwater flow. Again, we are looking at this area, large area, spanning over several thousand, hundreds of miles, hundreds of square miles in this region to model our system. So this shows model performance. Models did very well. Most of them were essentially within 1 meter. The difference, maximum difference we saw spatially was about a meter or less. And then that's very good prediction for a model that size for that large. And then these are some of the well hydrographs or time variation at individual locations, and we were able to capture that fairly well as well. And then you can see these are your model predictions and these are your errors. The red implies 5 feet error, and the green implies less than foot error. And these are the predictions that you see going from left to right, and this is a regional groundwater flow. So we can take groundwater flow model and then substitute a neural network. Training this neural network takes a long period of time. It is computationally expensive to train this network, but once we train this network, making runs with this network is very, very fast. So we could change the stressor, see what is happening. So essentially, we embedded the physics that we capture with differential equations, nonlinear differential equations, into a neural network, and then we were able to map that onto GIS. So we are able to create 2D, 3D surfaces using this types of models. So some closing thoughts. Natural resource management definitely is challenging because we are dealing with very complex systems. Understanding coupled human-natural interactions is very difficult, and you've got what is known as this decentralized management brings both aleatory and epistemic uncertainty. Aleatory uncertainty means basically statistical uncertainty or variability, and then epistemic uncertainty means we are not able to define the system very well. A lot of times there's a lot of discussions about where should the boundary condition be, where should our system be, how big should our system be, so on and so forth. Soft computing tools with GIS will further increase the utility of geospatial models for NRM. A suite of soft computing tools. I showed you lazy learners, collaborative learners, deep learners, all kinds of learners like tree-based learners. They can all be integrated within GIS. The best way to do integration is to use general purpose software such as Python or R. Usually ArcGIS, QGIS do have some capabilities, but they don't have as many capabilities as Python and R does. So, and Python and R both have some very excellent libraries for doing GIS type work these days. Plotly, Fiona, there's a whole bunch of packages in Python. R has what is known as SF package. simple features package that can do a lot of things, raster plots. So learning R and Python will open up a lot of these machine learning tools and GIS tools together, so it's a one-stop shop to put them together, rather than do GIS and GIS software, your analysis in another software, and then try to merge them together. So this avoids a lot of data, which can be expensive, and it can also avoid errors that happen during such data transfers. So that concludes. Sorry, I'm over by a few minutes, but I do want to thank Dr. Pasupuleti for this opportunity to talk to you all. And if there are any questions, I'd be happy to take them.